Welcome to this complete, exam-focused study guide for AI503 machine learning. We will walk through all 16 syllabus topics across 5 parts, from foundations to deep learning and reinforcement learning, covering essential formulas, worked examples, and likely exam questions. Here's the structure: 5 parts in syllabus order. Part 1 covers the foundations. Part 2, the classical supervised classifiers. Part 3, unsupervised clustering. Part 4, deep learning. And Part 5, advanced topics. Each part ends with an exam check slide of likely questions. Part 1, the foundations. Before diving into specific algorithms, you need to understand what learning means, the machine learning lifecycle, and the 2 workhorse models, linear and logistic regression, plus how to evaluate a classifier. Machine learning is a subset of AI that builds a mathematical model from training data to make predictions. The key is that the machine learns without being explicitly programmed, improving as it sees more data. This is a shift from traditional programming, where humans write every rule. The machine learning lifecycle has 7 stages: gather data, prepare it, clean or wrangle it, analyze, train, test, and finally, deploy. Remember, understanding the problem is the most crucial part of this entire process. There are 3 types of learning. Supervised learning uses labeled data to map inputs to outputs. Unsupervised learning finds patterns in unlabeled data. Reinforcement learning uses feedback from actions to guide an agent. Supervised learning splits into regression and classification, which form our first 2 parts. In supervised learning, the task depends on the output. If the output is a continuous numeric value, it is regression. If the output is a discrete category, it is classification. Note that logistic regression is a classification method, despite its name. Linear regression models a straight-line relationship between target and predictors. We find the best fit line using the mean-squared error cost function and gradient descent, which iteratively updates the coefficients. Logistic regression solves classification problems. It uses a sigmoid function to map values into a probability between 0 and 1. You can classify outcomes as binomial, multinomial, or ordinal. The derivation of the sigmoid from the linear equation is a frequent exam question. We start with a line, move to odds, then the logit, and finally exponentiate to isolate the probability. Remember the difference between odds and probability. To evaluate a classifier, we use a confusion matrix. Accuracy is calculated as the sum of true positives and true negatives divided by the total number of cases. Binary cross-entropy, or log loss, is another essential evaluation metric for training. For your exam preparation, ensure you can recall the 7 lifecycle steps, explain the sigmoid derivation and why we use logistic regression for classification, and be ready to compute accuracy from a provided confusion matrix. Part 2 focuses on classical supervised learning. We cover 4 key classifiers: support vector machines, k-nearest neighbors, decision trees, and naive Bayes. Each relies on a unique conceptual approach to classification. Support vector machines aim to find the optimal hyperplane that separates classes with the widest possible margin. The support vectors are the crucial data points that sit closest to the boundary and determine its final position. SVMs use either a hard margin for perfectly separable data or a soft margin with slack variables for noise. For complex, nonlinear data, we use the kernel trick to map data into higher dimensions. Common kernels include linear, polynomial, and RBF. K-nearest neighbors is a classic lazy learner. It builds no model during training. To classify a new point, you simply find its k-nearest neighbors and take a majority vote for classes, or an average for regression. All the heavy lifting happens at prediction time. Distance is how we measure similarity in KNN. Common metrics include Euclidean, the straight-line distance, and Manhattan, which moves along grid lines. Remember, KNN is sensitive to feature ranges, so always apply feature scaling. Choosing K involves a bias-variance trade-off. A small k, like 1, has low bias but high variance, making it prone to overfitting noise. A large K provides a smoother boundary but risks underfitting. Use cross-validation to select the best K. Decision trees are intuitive, non-parametric flowcharts. They use a root node for the dataset, branches for decisions, and leaves for the final class. Prediction means following the test path from the root down to a leaf. Trees are built by choosing splits that maximize information gain, which is the reduction of entropy, a measure of impurity. We prune trees to prevent overfitting, keeping the model simple and more generalizable. Naive Bayes is a probabilistic classifier based on Bayes' theorem. It assumes all features are independent, which is the naive assumption. It's particularly powerful for text classification, such as detecting spam emails. In practice, we multiply likelihoods for each class and normalize to find the most probable category. Beware the zero frequency problem, where a missing feature causes a 0 probability. The Laplace estimator fixes this by adding 1 to all counts. To master the exam, focus on the defining mechanism of each classifier. SVM uses maximum margins. KNN is a lazy learner. Decision trees are branching flowcharts, and naive Bayes is probabilistic. Understanding if they build a model is essential. For the exam, be prepared to compute Euclidean and Manhattan distances, identify which models are lazy, and apply the Laplace fix. Practice these concepts to ensure you can confidently contrast these 4 supervised learning methods. Now we transition to part 3, unsupervised learning. Here, we work with unlabeled data where no target exists. Instead, we allow the machine to group observations based on hidden similarities in structure. Cluster analysis aims to maximize intercluster distance while minimizing intracluster distance. It's important to remember that clustering is subjective. The number of clusters depends heavily on your choice of distance metric and parameters. Clustering methods fall into 2 main families. Partitional methods like k-means produce a flat structure of non-overlapping clusters. Hierarchical methods build a nested tree or dendrogram, allowing you to choose the level of detail after the fact. K-means is a 4-step iterative algorithm. Initialize, assign, update, and converge. We start with centroids. Assign points to the nearest ones, update the centroids to the mean of their new members, and repeat until stability. In an exam, remember that one iteration includes both assignment and updating the centroids. Use k-means++ for better starting centroids. And if you are asked to compute a centroid, simply take the average of its assigned points. Final review for part 3. Define the core clustering objective, distinguish partitional from hierarchical approaches, and verify you can trace a simple k-means iteration. This will solidify your understanding of unsupervised structures. Welcome to part 4, deep learning. This is where we go from single neurons to massive architectures, like transformers. We focus on how these networks learn features directly from raw data, building complexity layer by layer. Deep learning is a subset of machine learning using multi-layered neural networks. Deep means 3 or more hidden layers. The big shift here is from handcrafted features in traditional ML to automatic feature learning. The universal approximation theorem proves that large enough networks can represent any function. At the heart of the network is the neuron. Inputs are multiplied by weights, summed with a bias, and passed through an activation function. Weights amplify or weaken the signal, while the bias shifts it. Without nonlinear activations, the whole stack collapses into a simple linear model. Activation functions are vital. Sigmoid and tan were early choices, but suffer from vanishing gradients. ReLU is the standard today because it is fast, though it can suffer from dead neurons, a problem leaky ReLU solves. Softmax gives us probabilities for classification, and GLU is the go-to for modern transformers. Training happens in a 4-step cycle. A forward pass calculates the prediction, the loss measures the error, backpropagation uses the chain rule to assign blame to each weight, and the weight update nudges them using gradient descent scaled by the learning rate. We repeat this until convergent. Hyperparameters are key. An epoch is a full pass-through data, while the batch size controls how many samples we see before an update. For descent, mini-batching, sizes 32 to 256, is standard. Optimizers like Atom are preferred because they adapt the learning rate per parameter. The feed-forward neural network is our simplest model. It has no loops and is fully connected. It excels at structured tabular data like credit scoring or fraud detection. Regularization is critical here. Use dropout, L1, L2, or early stopping to ensure the model generalizes well. Convolutional neural networks are designed for images. They use sliding filters to detect local patterns. Key ideas include parameter sharing to keep weights low, translation invariance to recognize patterns anywhere, and pooling to downsample. Trying a dense FNN on images would require millions of unnecessary parameters. CNN history shows a trend toward depth. LaNet started it, AlexNet triggered the deep learning boom, VGG brought deep 3x3 filter stacks, and ResNet changed the game with skip connections. Those connections allowed us to train networks with hundreds of layers without gradients vanishing. Recurrent neural networks are for sequences like text or time series. They share weights across time steps, allowing them to handle variable length sequences. However, they struggle to link distant context because the same weights are applied repeatedly. RNNs suffer from vanishing and exploding gradients. When backpropagating through many steps, multiplying many small gradients shrinks them to 0, causing the model to forget long-term context. If gradients are large, they explode. We use gradient clipping to contain explosions and specialized cells to solve vanishing. The LSTM introduces a cell state acting like a conveyor belt, with 3 gates, forget, input, and output, regulating information flow. Because updates are additive rather than multiplicative, gradients flow much better, finally letting the network remember long-range dependencies. To summarize the LSTM, it uses a forget gate to clear old info, an input gate to add new, and an output gate to dispatch the result. Every gate acts as a differentiable switch between 0 and 1, allowing the network to learn exactly what to keep in memory. Compare LSTMs with GRUs and BI-LSTMs. GRUs are a lighter alternative with fewer parameters, making them faster to train. BI-LSTMs read sequences in both directions, making them incredibly effective for tasks like named entity recognition, where context comes from both past and future words. Finally, autoencoders compress data through a bottleneck to find essential features, training to minimize reconstruction loss. Variational autoencoders take this further, using a probabilistic latent space to generate new data, balancing reconstruction with KL divergence to ensure a smooth, usable representation. Transformers revolutionized sequence processing by replacing recurrence with self-attention. This allows all positions to be processed in parallel. The key attention formula uses a softmax of queries and keys to weight values. Other critical components include multi-head attention for capturing diverse relationships, positional encoding to track order, and layer normalization with residuals for stability. Generative models create new data. GANs use a minimax game where a generator creates fakes and a discriminator critiques them. Diffusion models, which power tools like DALL-E 2, add Gaussian noise to data and learn to denoise it step by step. We also categorize transformer architectures into decoder-only models like GPT, encoder-only like BERT, and encoder-decoder like T5. To help prepare for the exam, remember these 4 training steps: forward pass, loss calculation, backpropagation, and weight update. Be prepared to write the attention formula and explain how the additive cell state update in an LSTM protects against vanishing gradients. Finally, be ready to contrast the structural differences between GPT, BERT, and T5. This final section covers 3 advanced topics: ensemble learning, which combines multiple models, dimensionality reduction using PCA to handle large feature sets, and reinforcement learning, where agents learn to make optimal decisions through trial and error in an environment. Ensemble learning combines weak learners into a single strong model. The crucial distinction for your exam is this: bagging reduces variance by training models in parallel on bootstrap samples, while boosting reduces bias by training models sequentially, where each new model learns to correct the mistakes of its predecessor. Random Forest and Ada Boost are 2 primary ensemble flagships. Random Forest is an advanced bagging method that decorrelates trees by randomly selecting feature subsets at each split. Ada Boost uses adaptive reweighting. It starts with equal sample weights and increases the importance of misclassified examples after each round, ensuring subsequent models focus on the hardest tasks. The curse of dimensionality describes how the amount of data needed for a model grows exponentially as the number of features increases. High-dimensional data leads to increased training times, higher risks of overfitting when samples are scarce, and issues with redundant or correlated features. PCA is the standard technique used to mitigate these effects. Principal Component Analysis, or PCA, converts potentially correlated features into a smaller set of uncorrelated principal components. These components are orthogonal axes, ordered by the amount of variance they capture. The standard pipeline is to clean and scale your data before applying PCA, keeping in mind that PCA only captures linear relationships. Reinforcement learning involves an agent interacting with an environment. The cycle consists of the agent observing a state, taking an action, and receiving a reward or penalty along with a new state. The goal is to learn a policy that maximizes the total expected discounted future reward, often balancing the explore versus exploit trade-off using an epsilon greedy strategy. Q-learning is a foundational reinforcement learning algorithm. The update rule adjusts the Q value for a given state-action pair based on the immediate reward and the discounted value of the next state. The learning rate, alpha, controls the impact of new information, while the discount factor, gamma, prioritizes immediate versus long-term rewards. Multi-agent reinforcement learning deals with environments where multiple agents learn simultaneously. Interactions can be cooperative, competitive, or mixed. The central challenge here is non-stationarity. Because all agents are adapting at once, the environment from any single agent's perspective is constantly changing, which complicates the standard convergence guarantees found in single-agent learning. For our final exam check, remember that bagging targets variance while boosting targets bias. To compute image dimensions, multiply pixels by channels. When discussing Q-learning, identify alpha as the learning rate and gamma as the discount factor. And for multi-agent reinforcement learning, the defining obstacle is non-stationarity. Finally, here is the synthesis of our entire course. We classify algorithms into 3 branches: supervised learning, unsupervised learning, and reinforcement learning. Deep learning is not a separate category. It is a powerful set of tools that cuts across all 3, allowing us to build sophisticated models for any of these learning paradigms. This final slide is a formula cheat sheet. Key takeaways include the sigmoid function, accuracy, Bayes' theorem, the weight update rule, and the Q-learning update. Familiarity with these high-yield equations and their underlying concepts will be essential for your upcoming exam. Good luck with your revision. That completes the AI503 study guide, covering 16 topics from machine learning foundations to reinforcement learning. Remember to review your formula sheet, work through the exam check questions, and ensure you can map every algorithm to its core function. Good luck with your final preparations.